Hi friends, today we'll discuss the unit 4 of our compiler design course, that is intermediate code. See here, in compiler design we have 6 phases. First phase is lexical analyzer, second phase is syntax analyzer, third phase is semantic analyzer. Next, code optimization and code generation. So here the intermediate code generation act as a mediator between the syntax phase and analysis phase. So we'll see what is an intermediate code today. The intermediate code is a useful representation when compilers here the parser, semantic checker, intermediate code generator, code optimizer. It is here the role of intermediate code generator is after the phase of semantic analysis, it converts the given code into an intermediate code so that the code generation will be easy. So what are the benefits of the intermediate code is, if you converted in an intermediate code after the phase of semantic analyzer, it makes very easier for the target generation, the task. And it creates more and more compilers of the same source language but for different machines. So here when the compilers are running on different machines, the intermediate code can be easily converted into a target code. So here the intermediate code, so that we can say that our intermediate code is a machine independent code. Then only I can say so this code can be can be converted into any code generator not depending on the machine. Here to represent an intermediate code we use so many ways. Among that, for the first one is syntax tree, directed acyclic graph, postfix notation and 3 address code. Any of these ways we can use to implement the intermediate code. When we are going for the syntax trees, it is a graphical representation of our source program. So as if it is a tree, every tree will contain both a node and children. So here the node represents an operator and children of the node represents the operands. So it will construct a hierarchical structure will be constructed based on the semantic rules. So here the target code generated by, how will the target code is generated? As we know that the intermediate code should be converted into a target code. So if the intermediate code is of the form syntax tree, then the code is generated by traversing the tree in a post order. So for example, if you want to construct a syntax tree, here we'll use two things, that is node pointer, make a node and make a leaf. Okay, so here we are taking one grammar for a calculation of arithmetic expression. What I am having, the first grammar's protection is id equals to e tends to e1 plus e2, e tends to e1 into e2, e tends to. So here we are writing a SDT for our grammar. For what purpose you are writing here SDT? To construct a syntax tree. So here as soon as if the node pointer is like this, s tends to id, so you should make a node. Why? Identifier. We already discussed that in the previous slide. So node represents an operator and children of the node represents a operands, right? So here as id equals to e, it is a node. What you should know then s node pointer is make a node. Here id means what? Operand. So assign make a leaf id and place that id in en pointer, that one. Next, e equals to e1 plus e2. So you should make a node. That node should contain operator and its children is e1 node pointer and e2 node pointer. Similarly for this expression, you need to make a node with an operator and its leaves or children are node e1 and e2. Next, here we are making a node but its operator is for what? Unary. So it is a unary minus e1. And here just e is assigning with e1, so e pointer is equals to e pointer, and that e, for this we should make a leaf, e tends to id, we are making a, this is an SDT for constructing a syntax tree for this grammar. For example, we are taking one expression here, a is equals to b into minus of c minus d plus b into minus of c minus d. Now this minus indicates unary minus and this minus indicates normal subtraction. So here according to our statement, first we will make a leaf for ID, CD. For all identifiers, we should make a leaf. So, first node pointer P1, make a leaf for ID C. Make a leaf for ID D. Now, in between C and D, what is there? Minus. So, we should make a node with an operator minus for P1 and P2. Therefore, make a node minus P1 and P2. Now, for this, you need to calculate unary minus. So, here P4, make a node unary minus for P3 and next one is null, because for unary minus only one operand. So, next operand we will take it as a null pointer. So, every node will have three things. Okay, so first one is symbol, another one is operand 1 and operand 2. And this is an operator symbol. If it is a unary minus, operand 2 will be null pointer, so it will be null. Next, like that we completed which part? A minus B into minus C minus D plus B into minus C minus D. So, we completed this one and this is stored in which one? P4. Can I do same thing for this one also? P4. Now, how will be the expression? A minus B into P4 plus B into P4. Now, we should make an ID. So, instead of taking double, here they have taken again double term P7, P8 and they have done this one. Now, we instead of that, we can also take the same P4. Okay. We will see by taking double time now. So, here what is the expression? A equals to B into minus of C minus D plus B into minus of C minus D. Now, we completed this part. After that, we have making an identifier for, make a node for B. Make a, if for this operator it is a leaf, no, so we are making a leaf B. Next, we are making a node for this one. This expression. It is a leaf, it is leaf, now this is a expression. Again what I will write? P6 is equals to make a node. What is the first multiplication? B is taken by P5. Next, this part is taken by P6. Now, this whole part is done with P6. Again, you should make a leaf for B. So, here P7 equals to make a leaf for ID comma C, make a leaf for ID CD. Okay. Now, again minus for these two and unary minus. Now, this part is completed and it is named as P10. Now, how will be the expression? P4, A is equals to P6 plus B into P10. Now, you should make a pointer for this one. How I can paint pointer for this one? Make a leaf ID B. That one I am naming with P11. Now, what will be the expression? P6 plus P11 into P10. Right? Now, here we should do multiplication. Then how I will write? Make a node, multiplication, P11, P10. This then I am giving to which value? P12. So, for this example, if you constructed a syntax tree like that, we will get this one. Okay. Next, abstract syntax tree, removing all this, just keeping the symbols, then we will call it as an abstract syntax tree. So, this is the one of the intermediate code representation, that is syntax tree. So, next form is postfix notation. So, postfix notation is a linear representation of our syntax tree. How the syntax tree is represented? By using post order. Here, post order means we'll do like this: left tree, right and root. This is the post order representation. So, when you go to the abstract tree, what is left? For this equals to what is, this is root, left, right. So, left A. Next, right again you should come to left. For this left, right root. So B, C, D minus and unary minus, see, left, right, again right, left, left, right, root. This one completed. Root, no right. Okay. Then these two completed. What is the root? This one. So this left part completed, comes to right part. Again right, left. Now B. Next C. Next D. Next minus. Next unary minus. That is, you'll write unary minus. For this again, this. So this part come. Again coming to here, plus, then equals to. So this is the postfix notation for the given expression. So postfix expression is nothing but linear representation of a syntax tree. So how we'll traverse a syntax tree to represent a postfix expression is in post order we'll traverse a syntax tree. Next, one more form is what? Directed acyclic graph. Here, when you calculate the syntax tree, see, we are calculating 2 times C minus D, C minus D. So, instead of calculating these 2 times, we can take this result directly by representing a here. That if any common sub-expression is there, will show 1 time in directed acyclic graph. So this what it will do means the DAG will reduces the space and time requirement. In detail about directed acyclic graph in coming units we'll see. So this is also one of the representation of intermediate code. So here common sub-expression is what? Every time we are calculating this P3 C minus D and P9 also C minus D. So instead of taking these 2 expressions, for these 2 pointers we'll take a single pointer. So this showing the common sub-expression is possible in that. Next format is 3 address code. So mainly in our syllabus we'll focus on the 3 address code. So 3 address code is also one of the linear representation of syntax tree or direct DAG. 3 address, that means it indicating 3 sequences. The address code contains 3 variables at most. It should contain at most 3 variables. So the 3 address statement is like this: A is equals to B of C. So this is the form of 3 address code. Now, so here only one operator is permitted. If the expression is large, we'll break the expression in such a way that the break statement should contain a single operator. Then we'll perform the sub-expressions, then we'll calculate the results. So how we'll break the expression means based on the board mass tools. We have types of 3 address statements. So 3 address statements will be represented for differently for how the 3 address statement is written for different type of operators we'll say. See, if the operator is binary operator, then the 3 address statement is written like this. If the operator is a unary operator, then the 3 address statement is. If you want to copy one statement to another one, then A is equals to B. Now, if you want to go for unconditional gem, then we'll write go to L. If you want to do the conditional gem, if X, whatever relational operator, Y, go to L. Like this, we'll write the 3 address code. If you want to do any address assignments, like this. If you want to do pointer assignments, like this. Sometimes if you want to use an arrays like indexing, this is the format in the 3 address code. So if you see any of these statements, at most there are only 3 operands. I say in here 3 operands, 2 operands, 2 operands, 1 operand, 2 operands, 2 operands, 2 operands, 2 more than 2 operands are not allowable in 3 address statements. So that's why it is called as 3 address statement. By 3 here, 2 operands, 1 operator. So here up to now the basic statements how you can write we can see. Sometimes in our program we'll write function calls. So we'll see now how the 3 address code for functional call is represented. So here function call means what you'll have function name and parameter list, right? So here first we'll define a parameter list, then we'll go for a function call in 3 address code. Parameter A, call function, how many number of parameters, what is the return. See here we have one example. Here we have one function with parameters n and the return value is b. So I told you first we should represent parameter. So parameter a1, a2, a3 like that, parameter an. Then we should call a function. So call function, how many arguments? N arguments. Is this function is returning any type? Yes, return b. So like this the function call represented in 3 address code. Now these are all ways how to write a 3 address code. These statements can be represented in 3 forms, either in quadruple or triple or indirect triple. We'll see what is quadruple, triple and indirect triple. So here a quadruple is nothing but a record structure. Record means what here? It is a table of rows and columns. So here the table with 4 fields will take. So the first field is operator and second field is operator 1, operator 2 and result. Why this one? In a 3 address code we'll have operator, operand 1, operand 2. This result will write with one temporary name. This is a quadruple representation of 3 address code. So here we have one statement. What is the statement? A equals to B into minus of C minus D plus B into minus of C minus D. According to us, first what operation we'll do? C minus D. So T1 is equals to C minus D. Next we'll do unary minus for that one. T2 is equals to minus of T1. Next again for this you'll do C minus D. Again we'll go for this. T4 is equals to C minus D and T5 is equals to minus T4. Minus T4. Next this part is completed. So this is stored in T2 and this is stored in T5. Now we need to multiply B with T2. That is I am taking at T6. T6 is equals to B into T2. Next T7 is equals to B into T5. Now how I got this result we got and this result we got. Now we should add T6 and T7. So here that one I am taking in one another T6 plus T7 and this again should be given to A, no? So equals to T7A. That's the thing here. Okay. Next. So in quadruples there is an overhead for managing. So say many times you are having many temporary variables. So here to reduce the names unnecessary temporary variables we go for the triple representation. So triple in quadruple we have 4 fields. In triple we have 3 fields. For operation and remaining 2 operands 1 field. So here operation, operator, argument 1, argument 2. So here this operation result will be stored in a position. So here 1 for the operation, remaining 2 for, and they may have a variable or constant. The position number will indicate the computed value. So instead of taking a temporary value, that position will directly take in this one. This is the triple representation. So here first operator is minus C D. That position we are giving it as 0. For this I want to apply unary operator U of 0. And for this we are applying again B into this one into B of 1. Next minus C into D. Next unary minus. for this third position, and that third position is stored in fourth. That fourth is multiplied with b and stored in fifth. Now whatever result is there in 2 and whatever result is there in 5, we should be added. So 2 plus 5. Next, that should be equal to which variable? A. So A. Indirect triple. So here indirect triple means here we are list offing the pointers to triples. So here we'll do the operations. Every operation will list one pointer and will provide the sequence. First should be which sequence? First C minus D, no? So 0 sequence. Second U of 2, 21. Third, like that. So we'll do what are the sequence of operations. So indirect triples means first giving the pointer to that location, that pointer you are referring. By this, we completed the 3 address code, intermediate code forms. So here, we just recap here. Intermediate code is a mediator between the syntax and analysis phase. So here, the intermediate code can be represented in any of these forms: syntax tree, directed acyclic graph, postfix notation, and 3 address code. Syntax tree is a graphical representation. To construct a syntax tree, here we use 2 functions, make node and make leaf. By using the make node and make leaf, you will construct a syntax tree like this. So if the tree is like this, we will call it as abstract syntax tree. This representation is a syntax tree. This representation is an abstract syntax tree. Next, the linear representation of this syntax tree, will call it as postfix notation. How postfix notation will be done? If you traverse the syntax tree in post order form, then we'll get the postfix notation. Directed acyclic graph is also a diagrammatic representation of the syntax tree, but in directed acyclic graph, the graph is represented by eliminating the common sub expressions. Next format is 3 address code. So 3 address code can be represented in one of these 3 forms: quadruple, triple, indirect triple. In quadruple, it is a record of 4 fields. First field is operator, operand 1, operand 2, result. And the second, in triple, we have only 3 fields: operator, argument 1 and argument 2. For every implementation, we will give a sequence. Next, here indirect triple will indirectly go for the statement by referring the pointers. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.